Welcome to the next lecture on formal verification, which was the part of the course on optimization techniques for digital VLSI design. So, in the last lecture basically we were trying to see how we can model large scale systems using binary decision diagram. That our motivation came from the fact that verification requires explicit modeling of the systems, and if you are using a straightforward state based representation due to the exponential nature of the state encoding, the system's size blows up. So, we were trying to see basic exciting data structure called binary decision diagrams, and we are trying to see how it can drastically bring down the size of any binary decision tree yet not losing any information. So, in the last lecture, that is on the binary BDD based verification, as a two lecture module, two lecture structure, because it has quite a lot of material to be discussed. So, what we have seen that basically that if we are given a binary decision tree, then how we can actually compress it using a BDD without losing any information. And it was very interesting to find, I hope, that in any binary decision tree there are a lot of redundant nodes which can be easily removed, and so that the redundancies are gone and you can get a very efficient representation which is nothing but a BDD. But then where we stop? We say that given a binary tree, we have to how we can reduce it to a binary decision diagram is what we were discussing. That was to show you that what is the compressive power of a BDD, or in other words what is the amount of redundancy that is in any binary decision tree. But if you tell me that I have to design a BDD in that manner, it is not a very good idea to do that. In fact, it is impossible to do it that way. Why? Because if I am giving such a big tree and then you are compressing, and if the size of the tree is the order of 2 to the power n, where n is the number of system variables. So, it is impossible to build such a big tree if the input variables are 20 or more than that, a typical number. Then it is a foolish idea that first I blow it up and then I compress. So, that is not a very good idea or an infeasible idea to do it in that way. So, today what we are going to see is that we are not going to go for such an approach. Rather, what we will do, we will have small atomic BDDs and then we will merge them so that you can get an entire BDD which will represent the total function or a circuit, which is a more logical way of doing it. That is, we will try to build up the structure so that it does not grow big at any point of time, because the other way around, that take a binary decision tree and bring it to BDD is not a possible way of handling the solution. Then we will see that binary decision diagram basically always follows a bit level structure, and whenever we have discussed about testing in the last module, we have seen that whatever you do, whatever optimization you do, if you are working at bit level, you cannot go higher than a certain range. So, the need of modern day VLSI systems like NOCs and SOCs, you cannot think of any representation in terms of bits. You have to go to words or you have to go to integers, and which is more abstract view than the bit level circuits. That is, we were mainly looking at the RTL level diagrams or RTL level circuits. So, in case of BDDs also, we have to move to higher level of abstraction like arithmetic decision diagrams or high level decision diagrams, which are actually nowadays used in place of BDDs to represent large scale systems like NOCs and SOCs. The idea is, even with BDDs, you cannot handle such large systems. So, the ADD and HLDD based optimization, and there are so many other decision diagrams like ZDD, etc. But we will see the most important two of them, that is ADD and HLDD. Basically, they will show you how you can abstract out until you can go for a much larger system than that can be even conceived by a BDD. So, we will now quickly basically go to basically where we had left last time, that we already discussed that how we will go about constructing a BDD from the binary decision diagram and tuning it down. But now we are going in the other way around, where we will be doing it from the roots. So, basically what it says, the ROBDD for the output of an AND gate. So, we are taking the output of an AND gate, so which is actually which we can compute by the ANDing of the two BDDs for A and B. So, as I tell you, A and B are two variables. So, what will be the BDD look like? It is as simple as something like that. A0 is 0, A1 is 1. For any single variable, the BDD will be looking like this. B equal to 0 means 0, B equal to 1 means 1. This is the simplest way of representing a single variable in terms of BDD. Now, what you can do? So, this is the AND gate. Now, how can we do that? So, the second point says ROBDD for the AND gate can be constructed by first determining the Boolean function at the output, that you find the Boolean function, then construct the ROBDD using Shannon's expansion. That in another way we can say that basically you go for the binary decision tree kind of a diagram and then tune it down. But construction of ROBDD using Shannon's expansion is cumbersome because of the large size. So, this is an AND gate, so it is trivial, but if you think it's a very big circuit, so you will have a big Boolean formula at the output, you have to do a Shannon's expression and you have to make it. That will not be a very good idea to do it. That is something like you are having a very big binary decision tree and you are pruning it down to a BDD. That is not a very good solution of doing it. Rather what you should do, rather basically you should try applying operations on binary decision diagrams, like we will have one BDD here, one BDD here. We have to go for an AND operation. We should have the provision of ANDing the BDDs, and finally we should have a reduced BDD something like this, which tells that A equal to 0 means 0, A equal to 1 means you have to check the value of B. If B is 1, the answer is 1, else the answer is 0. So in fact you have to get this final BDD by operation on these two BDDs, not by the way that for a very given big circuit you basically have the Boolean expression and then go for a Shannon's method of expansion and going for the BDD generation, which we have discussed in the last class. You should not follow that, but why we are discussing all these things in the last class? To give you an idea what is BDD and what is the power of BDD, how much compression it can do. So that was the idea, that is why we were showing it in the last class. But practically computing a BDD, you have to go from the leaf level. A very big circuit is there, you take all the input BDDs which are of this form, then you go for BDD operations and finally make the final BDD for the large circuit. So for that it is very important for us to understand how BDDs are operated, that is BDD A plus BDD B, BDD A dot BDD B, BDD B complement. So all Boolean functions we do like AND or XOR NOT, bar, all these things are possible on BDDs. So that is why it is not only about the compression power of BDD, rather there are so many interesting features of BDD that has made BDD, and in fact we should be very thankful to Bryant for finding out such a wonderful data structure. So basically obviously it is compressed. Secondly, you can do all Boolean operations on BDDs, that is another good thing. And third is basically canonicity, that if all the ordering is same and if the function is same, both the BDD will be, or the functions are equivalent rather, both the BDDs will be identical. So that was the three basic features which make BDD as the most important data structure for VLSI and digital design. So now we will show you very simple way of handling BDDs. So complement. So what is the complement? Very simple, it's extremely simple procedure. If say we are considering that there are the two BDDs, I am not drawing the internal structure, this is BDD 1 and BDD 2. So if I just take this BDD BF and if I just reverse the values, that here that these are two BDDs, I mean I take the two values of two BDDs, so be the BDD F and BDD G. Now I will do some operations on that. So if I want to make, because this BDD BF, BDD G are the two BDDs we will be considering in this lecture to show all the operations. First one is complement. So how do I complement? Extremely simple, the most simplest of all operations. So this is your BDD F and G 0 1 and 0 1. In compression, in negation what you do, you just reverse the terminal nodes or make the values of the terminal nodes flip. Obviously the whole circuit will be, or the whole output will be a complemented output. Entire BDD will remain same, the complement operation will just make this node 1 and this node 0 and so on. So just you need to change the leaf node values, then the BDD will be complemented. So it is simple, the BDD is for the complement, it is very simple, you just need to reverse the values of the leaf nodes, that is what is being said. So it may be noted that the complement BDD on RO BDD would result in a BDD that is ordered and reduced. One very important point I have to tell you why it has such a meaning. One bad thing about the operation is that if you operate two BDD, the output of the BDD is correct, but it may not be the reduced one. It may have some redundant nodes. So because I mean there is no direct way, people have not been able to find out any direct way of operating the BDDs so that directly you can get a compressed BDD or the most optimized BDD without redundancies. So what we have to do? You do the operations on the BDD and then you have to eliminate the redundancies explicitly. But one thing you have to note that the redundancy will be very slight, only a few amount of nodes will be redundant. It will not be like that you operate two BDDs and it will become a binary decision tree. That will not happen. Slight few number of nodes will become redundant, which you have to eliminate out, and then it will actually become a BDD. So again repeating, take two BDDs, operate on them, you will get another BDD, but that BDD will not be ordered, it will not be reduced, but the ordering will be maintained. That is very important. That basically the ordering means if you have A, B, C, D in the one order, and one more important thing I have to tell is that when you are operating the two BDDs, you have to maintain the order. Ordering is very important. So whenever you think of operation on BDDs, a common ordering you have to maintain across all the functions and all your jobs you are doing. So ordering of the variables has to be same. Under that case, if you are doing any operation, excepting the complement we are discussing, for all cases it may happen that the BDD, some redundant elimination nodes may go into picture. But that will not be very high in number, that will become something as used like a binary decision tree. That will not happen. So you have to do slight tuning off and few nodes will be eliminated and you will get the finally reduced BDD. But in case of complement, it is a very simple operation, just you are flipping of the values of the leaf nodes. So in that case the order will be also maintained, order is always maintained basically, and it will be a reduced BDD. You will not have any redundant node coming into picture. Once I will go for some other operation, you will find out why some redundant nodes may come up in a other operations. But for the complement, just think the idea that you are just reversing the value of the leaf node, so nothing changes, very simple operation, ordering of variables remains same in all operations basically, not only this, but a special case of complement operation is that the BDD remains reduced. Now things will start becoming more clear, why redundancy comes basically. So we are now talking about two more BDDs, that is AND and OR. So two BDDs are there. How I will do on and on OR, you can read these slides, they are just about what I am explaining, I have written them in text for you to read. So just see this. So this BDD, what it says that this is BF B OR, this is the OR BDD. So BF1, and I am just taking the left node, that is the 0 part of BF, and I am connecting BG and I am just attaching it directly. So what it implies? If it implies that if BF is equal to 1, then output is equal to OR operation. So if any of the BDD is giving answer 1, the answer is a 1. But if the first BDD is giving answer 0, then what? Then basically you have to check for second BDD. If the second BDD is also 0, the answer is 0, else the answer is a 1. So now you see, it's a very simple way of handling. Take two BDDs, ORing basically makes such a similar structure, that basically it will be connected like this. Of course the ordering will be, you have to obtain a common order whenever you are taking both the BDDs, the ordering should be maintained. I will give some examples when that will become more clear, but here you can see redundancy comes in. So how the redundancy will be eliminated? You have to have basically, you have to remove this node and you have to connect this one to eliminate the nodes. So not only at the leaf level, internal levels also many redundancies will come in which has to be eliminated, but there are limited number of nodes that will become redundant. But anyway, just this gives you an idea how it happens, and if it is an AND operation, then if any of the BDD is a 0, answer is a 0. If first BDD is a 1, you have to check for the second BDD. If that is also 1, the final answer is a 1, else the answer is a 0. So now you can see two redundant leaf nodes. Internally also some redundant nodes may be there which has to be eliminated, and then actually get the reduced order BDD. So idea is that you do not go for n number of operations. Like for example, you may have to do A plus B plus C dot D. You do not do the whole computation and start reducing. That will actually blow the complexity up. You do one binary operation like two BDDs, you will get another BDD which may not be reduced, reduce it and then go for the second operation and so on. So at any point of time you are not allowing the BDD to blow up. So you do slight redundancy gets in, you remove it, then go for the operation with the third operand and keep on doing it. And after every operation you eliminate the redundancy. So at no point of time you will have a very large BDD and your complexity will always remain with bounds. So what I am saying, that whatever I have told you is written in this one. In case of F plus G, if F is 1, then we did not evaluate G, and if A is 0, the final result depends only on G. This is reflected by the BDD for F plus G. Similarly, dual will happen if it is A for G. So now you can see the way we are constructing BDDs, it is clear that the BDDs are not ordered or not reduced. So basically the idea is that BDD F may have variables x1, x2 and x3, and BDD G may have variables like I, J, K, L. So new variables may come in, so the ordering may be changed. Change means orders may not remain same, that is what they are trying to say, and obviously redundancy is lost, redundancy gets seen basically. So you have to take care of this. When I am saying that the ordering is not maintained, it says that it may happen that BDD F may have variables A, B, C, and BDD G may have variables A, B and F. So new variables will start coming in, and so ordering may be hampered. So new variables will be there, so you have to reduce it and you have to take care of the new ordering which may be A, B, C and F. So that we will take more concrete examples to do it. So basically this is a mathematical way of using the BDD operation called apply, which is the most important one, because complement is just a bar. Apply is you actually take two BDDs and do the operations. So the formal way of writing is apply of BF BG. BF and BG are two BDDs, the reduced order BDDs, and operation is add, dot, XOR, etc. And the Shannon way of representing is, you can just see over here. So f of G is nothing but equal to x bar, the expression f with x0 plus x with the expression x expressed as 1, and similarly for G. And when you are going for the operation, the Shannon's expression value is x bar, f of G with x with x made 0 of same operation, add, star, whatever, G with same thing, all the variables in function G are made 0, and then x with f where all the x are made 1, operation with G where all in function G all the x's are made 1. So basically this is Shannon's way of representing, and then basically we will now tell you this is the mathematical way of representation. Now we will basically tell you the algorithm how to basically go for operating two BDDs. So basically they say that this is the control structure to apply, which proceeds from the roots of B and G downwards to construct the nodes of BF operand BG. So basically we start with the node, and then this Shannon expansion basically tell that you have to keep on moving from the top node to the root nodes, just like already we have seen that we first make x equal to 0 and keep the function at the left part, and make x equal to 1, do it at the right part. Now with the operations the same thing will be done. We will give you all the elaboration with examples. So we are assuming that let RF be the root node of BF and RG be the root node of BG. So we will start with basically the root nodes. So now this algorithm, so I will just give you the gist of the algorithm, then we will take an example which will make it more clear. The algorithm is on the screen, please read it because more means understanding of the algorithm will come when you go for the example and then coming back, but I will give you the gist. So what it says, apply, we will go stepwise. So it says that apply BF BG, so this is the algorithm. So for the first step you have to see if both RB and RG are terminal nodes with some labels LF LG, that is 0 or 1 respectively, compute the value of LF LG. That is, we are starting with two nodes, basically say node this is called RF and this is called RG. So let them be two terminal nodes, maybe 0 or 1. Then what is, maybe this is basically 0 and this is basically 1. It may happen. In that case you do not have to do anything, just take these two nodes and operate. If it is AND, answer will be 0, if it is OR, answer will be 1 and so forth. If it is XOR, the answer will be 1 and so forth. So and the resulting is the resulting OBDD is B naught if the value is 0 and otherwise. So in that case you will have a concrete node called 0 or 1. The final answer will be B1 or B0, that is the final answer for this operation if both the nodes are basically RB and RG are terminal nodes. So this will happen when your algorithm will terminate, because the way we will do the BDD operation is that we will take two nodes, one node from this tree and one node from this tree, and finally we will stop when both the nodes are basically the your terminal nodes, and that time the algorithm will terminate. Basically 1 is for termination of the algorithm. Next, the other cases which will maximum happen, in the remaining cases at least one of the root node is a non-terminal. That means you have two non-terminals, or one is a terminal and one is not a non-terminal. That is, at least one of the non-terminal nodes are there. Then they say, you just look at this, if both the nodes are Xi nodes, that is non-terminal. If both the nodes are non-terminal, we are taking a node Xi, we are calling it as RF. Okay. If both the nodes are Xi nodes, that is, you are taking two nodes, say basically we are taking maybe RF, sorry, we are taking both are Xi nodes. So when we are calling both the nodes are Xi node, means both are non-terminal nodes of the same order. That means it is saying that if that is step 2, it is saying that if both the nodes are Xi node means non-terminal nodes of the same order. That means say I have a node called RF and another node called RG, two belonging to two different trees. Say they may be both X3, maybe X4 or X5, that is they are in the same order, because when I am talking of operating of two BDDs, the ordering should be maintained. It is something like that both are of the same order. In fact, they are the same level nodes. So basically what you do, if they are of the same order, then what you do is that basically you take corresponding to this, you have a node, and then you will go for this part, which one will be equal to RF. So low of RF into low of RG. That means the idea is something like this. This is for, this node is for first BDD and this node is for left BDD, second BDD. And RF and RG, assume that they are at the same level. That means either X1, X2, X3, something like that, not at different levels of the ordering. Then what you do? You have to make another node which will be the resulting of this node. What will be in that node? That node will basically, the left, I am making the left node first, because we are combining the two nodes. So what will be the child, left child corresponding to RF and RG? It is something like apply operation, add or subtract, lower part, the lower child of RF and the lower child of RG. So basically this new node will come up, which is actually corresponding to the lower child of this, that is the left child of this, sorry, the left child of this, and it will also have a left child. So both the left childs you take, go for the operation, and this one will be resulting in the child node corresponding to RF and RG. And of course this one will come for the corresponding to the left child. Similarly, you will have a right child corresponding to RF and RG. So what will be that? That will be the operation on the node which is in the right side of RF operating on the right side of RG. So that one will correspond to the apply of high of RF and high of RG. The logic is very simple. Node A of this tree, node B of this tree, same level. Okay, now what you do? Corresponding these two, there will be a left child and a right child. How to get a left child? You take the two parent are there, you take the left child of both the node, both the parent node, operate them, it will become the left child corresponding to that node, that is 0, 0th value. And then similarly for the right child, that is you take these two nodes, take the right hand child, there is 1 for the parent nodes, do the operation and you will find out the right hand child of the parent node. That is the solid line. So 0 and 1 you can do it. That is very simple. That means it says that if you have two nodes at the same level, compatible nodes at the same level, this side will be the these are the two nodes, the child node of the operating final BDD will be the AND or whatever operation of the two left childs, and the right hand side of the final BDD will be the operation of the right hand side nodes of the two parent. That means these two go to the left, operate, you are going to get the left child in the resulting tree. These two parent BDD same level, go to the right child of both the nodes, operate them, you are going to get the right child. After operation you will get the right child of the in the parent tree. But that is what they are saying, apply of law of RF, law of RG, and right side means that is the 1 is the operation of code, or means the operation high of RF, that is high of the parent and high of the second parent. This is simple if the two nodes are of the same level. Problem will happen if basically you have something like, say, there is a node RF and there is a node called RG. These are the two nodes in the two trees. But you see J is greater than I. That means the level of RJ is higher than the level of RF. Then what is you are going to do? Because if they are same level, it is simple. You take both the left child, operate, take both the right child, operate, and you are done. But here actually you have to do it in a slightly different way. As RF is slightly above towards the root. So what you will do? You will operate, but you will not take the child of RJ, because RJ is always in the lower side. RF is in the upper hand side of the tree. So you will not operate the right child of RF with the right child of RJ. You will not do that. Rather what you will do? You will keep the RJ constant and try to operate from the right child of RF, then again the right child of RF, then again the right child of RF with RJ. You will keep on doing it till the level becomes equal. So what you do? Operate lower value of RF, that is corresponding to the left, and you operate with RG. That is basically this RG you are going to operate on. And basically, in fact, I was saying that it is basically RG, not JRG basically. So for all such G's, and in fact, when you are going to get the right child, you will apply of code high of RF, basically that is the right side of RF, but you are not going to take any child of RG. You will repeat it as long as both the levels are equal. So what happens basically, just look at the mathematics, you can read it, I will just give you the gist what is happening. RF at the top, RG at the bottom. So you are going to take the left child of this, operate with RG, you will not use the child of RG. Similarly, for the right side, you will take the child of RG, but operate directly with RG. You are not going to take the child of RG, because RG is quite lower in place corresponding to RF, height from the tree, from the root. So the number of depth of RG is much low, means this is this is the root, here you have RF and below is RG. This is something like this. So RF is at a higher level. So what is happening is basically you have to bring them to the similar ordering level, then only you can operate. Before that, you have to just take the one which is more near to the leaf node or which is more farther away from the root node, that you have to keep constant, and you have to take the left child, right child of RF, which is more towards the root, so that they come to a compatible level. So similarly, it can be simultaneously done like what it is saying if RF and RG are vice versa. So this is actually symmetric. So in gist what happens? So in gist, take two root nodes, then if the nodes are at the same level, you take the left child of this, final operate, get it. Right child of this, done. You keep on doing it as long as it will terminate when you operate to terminal nodes. But it may always happen that one node is more towards the root node in one tree, and the other one will be more towards the leaf node, that is levels are not similar. Then what you will do? You take the child of this node, operate on this, do not take the child of a lower level tree, a lower level node basically. Similarly, you keep on doing it till they come in the level. showing with an example. That is the gist. You keep on doing it. Now I will give you with an example which will make the things very clear. So this is the tree, I think you can see, and you have to do basically an OR. So what you will do? You will just tell me that x1 and x1, these are the two nodes, name is R1 and S1. Just I will zoom it for you. So you can see they are zoomed versions, R1 and S1, both are x1. So at the same level, so the operation will be very simple. You are going to have a node called R1 S1, which is basically nothing but you have to operate. Now you are not going to get it, that is the OR, you are not going to get any answer because they are both the non-terminal nodes. Next what? Next I am going to take the two nodes, basically, sorry, this is the root node, fine. Now what you are going to do? Now you have to operate on, so this one is the starting point. Now I have to keep on doing it. Now basically, say I have to operate, now I will going to show you the structure. So this is the R1 and S1. So this I am already gone, done. This is the root node, both are the same level, so this is done. Now you just see the next is R2 and S4. So next I have to find out, so this is the root node corresponding to the tree. Now I have to say that I have to find out the next level. So what is the next level? Here it is R2 and here it is S4. You can see this is the terminal node. So it is S4. Till now it is fine, but now there is a problem, there is an issue. Now till now at this point the levels were similar, both were at the same level. Now I am coming to another level where there is a level difference. So what is the level difference? It is saying that it is R2 and this is S4. So the level difference will start coming up from here. So next is I have the next is basically R2 is the left child of this and S4 is the right child of this. So you get a node over here. Up to it is fine. Now if I start going for the higher next level. So next level what you are going to see? You are going to see that this is x2, that is nothing but R2, and S4 that is your terminal node. Now there is a level difference. So now you cannot do like previous step. Previous step what you have done, as x1 and x1 are at the same level, that is R1 and S1 at the same level. So you are taking this and you are going to take this and you are going to find out a node called R2 S4. But now you cannot do like that. Now what is going to happen? Now as I told you, the S4 is always at a very lower level compared to R2. So now the next one you are going to have, these are all dotted lines, left ones are all dotted, just take it. So now what is going to happen? Now you are going to have from R2 you are going to have R4, that is the left. But here I will actually not go, even if it is a leaf node, but what I will do is that I will not take any left or right, rather I will keep it as S4. That is, here I am taking the left child, but here I am keeping a constant at the constant level, because in the second tree I am always further down in the level, but here I have to come down. So it will be R4 and S4. So here I will come over here, but here it will be remaining over there. Next, from here also you are going to take the value called left, so it will be R6, sorry, it will be R6, and of course it is going to a left child, but here actually is a leaf node, you cannot go at any left child, but assume that if you, even if it is further upper in the level and it is a non-terminal node, still as x3 is at a higher level corresponding, towards the, if you are higher level means it is more towards the root and it is more down the leaf. So you cannot take any left or right child from here till this first tree actually comes to the same level. So as of also it is not coming to the same level. So from R4 you are going to go to R6, but S4 will remain constant because x3 is more near towards the leaf compared to the S4. So now both of them have come to a leaf level. Now you can do the operation. So 0.0 is nothing but equal to 0. So this is actually computation, but more importantly to emphasize that it may not be a terminal node, it may be some non-terminal node also. In that case you are going to have R6 and S4. Now next step you may have, if you have something like this, then these two nodes, these two paths will be operated on and you are going to get a new tree, new node. Again repeating quickly just a gist what we have told you, that you have to always maintain the labels. Operation is very simple. First you will start off with the leaf nodes, root nodes, they are similar level, so no problem. Secondly, you are going to have a path of combination of these two, that is the left child of x1, that is R2, and the left of S1, that is S4, you are going to have a node like that. After that the interesting things come, because S4 and R2 are not at the same level. So what you will do, the next node will be R4 combined with again x4, because they are not in the same level. Next what you will do, again you are going to take the left of x3, and still it will be the S4 only, because now the levels are same. Now you are going to do an operation and you are going to get the value 0, but had it not be a terminal node, after reaching this, if I consider this a non-terminal node, then from here you could have taken the left of this and left of this and find out a new node. So you have to wait till the levelization happens. And but if you reach a terminal node, so you have to stop over it. Very simple over there. So in fact, this part will be very similar. You will have a single node structure over here, both x3. So the right hand part will be operation of R3 and S2. At x3, you are going to have a similar level. So both this left and this left will be there. Here you are going to have a right node. So the levels are same. So there is no at all a problem. The right path, there is always maintaining a level, same level over here. So there is no question of any waiting. The operation is at the level by level. But in the left part, as I have shown you, till you maintain till both the operating nodes come at the same level. So here the ordering level means ordering. Level is 1, 2, 3 and 4, and then root basically. So you have to wait till both the levels are come. Otherwise, one guy only will come down and other has to wait till there. So this is the structure. So R1 and S1. Then next is R2 and S4. So this one basically this is the tree. R2 and S4. Then again this one is R4 and S4. So as I told you, so this is R4 and S4, and then finally R6 and X4. That is R6 and S4. Now the levelization happen. By chance this is both are terminal nodes. So and 0 and 0, the answer is a 0. The right hand side already I told you, it is a very normal way of building the tree here. So you can see the right side is R3S2, same level. So it is R3S2, then this is R5 and S. So it is R5 and S3. So similarly this is this is R5 and S3 is this stuff, and then again it will be R6 S4. So same level R6 and S4. So both are basically 0. So 0 or 0 is answer is a 0. So this is a 0. But if you take the right side, so that one is going to become R7 and S5. So R7 and S5, that is equal to AND of 2 ones. So the answer is a 1. So this is how the tree will be built up. BDD will be built up. Now here you will be finding out that there will be lot of redundancies. Like so many leaf nodes will be similar ones will have come up. So that you have to reduce. In fact, you will find out that if you try to calculate, many of the basically the internal nodes will also be redundant. Like as you can very easily I can see that maybe this part and this part looks somewhat similar type of BDDs. So all the redundancies you have to eliminate. Typically the leaf nodes would very have redundancy. This part and this part more or less similar. So I can have a path from here to here. So all the redundancy steps you have to eliminate now. Then you can go for another operation. So as I have shown you, the way of operation is very simple. Take two compatible nodes, do the operation. Non-compatible nodes means non-levelized nodes. You have to keep on doing left, right till the operation comes that when both the nodes are at the same level. So if some is lower in the level to the root, only the left will come, then it will have the same level, then you can again go on repeating with the same level of operation. So this keep on going as the tree you have done, and finally whenever you will have both the operating nodes are terminal nodes, then you get the values and you stop. But there will be a lot of redundancy inculcated in this process, like many leaf nodes will come up. Internal node structure as I have shown you over here are redundant, so you have to eliminate the redundancy. One very important thing as I tell you here, you have to reduce all the redundant nodes at operating any two BDDs before you go for operating with the third BDD, because if you keep the redundancies, things will keep on blowing up. So you operate, reduce, operate, reduce, this way you go. So at no stage in time you are going to have a very big BDD. That is what is the idea of BDDs. So whatever I told you in English is written in the slides, like say for example how we have taken R1 and S1, then by step 2 of the algorithm, in which case both the nodes are levelized. So you operate R1 and S1 and you are going to guess the next child, that is basically equal to R4 and S4. So whatever I have told you how the operations are done, and if the input is this, you start with R1 and S1, that is the root node. So you are going to get the root node like this. There's basically R4 and S4, how do you get? R4 and S4 you are going to get if you are operating step 3 on R2 and S4, because basically S4 is the node which is quite down the level compared to, S4 is more down to to the leaf node compared to R4. So R4 will R2 will change to R4, but S4 will remain constant. So which is the step, algorithmic step I have used, that is step number 3 and so forth. So this slide basically tells you whatever I have told you, that what are the operations being done, that it is saying that off of low of RF, but RG is keeping constant, because you are going to take the left child right child of RF, that is nothing but R2, but S4 is keeping constant because it is down more towards the leaf node. So we are going to operate OR on R4 and S4. R4 is nothing but the left child of R2, but S4 is remaining a constant. So whatever I told you, the steps, how they are, some of the steps have been illustrated in this slide. You can read it. This is just the mathematical representation. You can easily correlate. So this is the final low BDD. As I told you that there was some similar looking structure in the BDD. So I have eliminated the 2 similar looking BDDs, that is the sub BDDs which were similar, and I am going to get a final reduced order BDD. Now I can do another operation on this, that is not a problem. It will again may have some more extra redundancy. If I do another operation, you eliminate and keep on doing it. So that is what is the idea of BDD construction using operations. You have a very big circuit, take a gate, take the inputs, construct the BDD for the output of the gate. Reduce the redundancy there itself. Then you can take another gate in the forward and find out the BDD for the next level of gate and keep on doing it. For every gate computation output of BDD, you have to reduce it at that stage only. It is not like that you will compute for 2 or 3 gates and then reduce at a time. If you do this, the intermediate BDDs will become very large in size and your whole idea will be lost. Then one more interesting operation on BDD is called restrict. So restrict means basically you want to see, if I make one variable 0, how the BDD or what are the binary function looks like. If I want to make one variable 1, you can ask many questions, like if this variable is 0, then what will be the BDD, or what will be the binary Boolean function look like? Can it still be 1, and if it is still 1, what variable has to be 1, and so forth. Like if we want to say that these 2 BDDs are not equivalent, or these 2 functions are not equivalent, but what if I make y equal to 0? For example, I assume that for a certain circuit or a system, the y is always 0. Under that circumstance, whether the 2 BDDs become equivalent. So that is some very important operation in final verification, which is called restrict. In restrict means you stop the value of a variable at 0 or 1 and try to study the BDD itself. So that is actually called restrict. So restrict 0 or 1. So if I want to say that I want to restrict x to 0, so what we have to do? So if there is any variable called x node corresponding to this, you eliminate that node and redirect all incoming edges to low of n. So if there is a variable called x, node x, so this may be the lower path, there may be another node called y. So all you have to eliminate this, and all paths coming to this node has to be redirected to the left child of x. That means because this one is eliminated, because I will not consider any BDD or sub BDD which corresponds to y equal to x equal to 1. So I will eliminate this and all edges I will redirect over here. Similarly for the restrict 0. In restrict, so basically this is restrict 0. So I will do it in this one. Restrict 0 means you want to study the value of the Boolean function if x is equal to 0. If you want to restrict it to 1, that means I will make x equal to 1, then I want to study how the BDD looks like. As the example I have given you, that 2 circuits, whether they will behave similarly if one input is stuck at 1. Stuck at, or in this sense I restrict it to 1 because I know that that is the reset line, and the reset line will always be equal to 1 for certain purposes. So under that circumstance, whether the 2 circuits are equivalent. In that case, basically you go for the restrict operation. So basically in restrict operation, we take the node which has to be restricted, eliminate it, and all the incoming nodes will be directed to the left child or to the right child, depending on whether it's a restrict 0 or whether it's a restrict 1. Example, like this is a function, and I want to basically apply x3 equal to 0. That means I want to see if x3 is equal to 0, how the circuit will be or the function will look like, and so forth. There can be different purposes. How to do that? So basically what they will do, they will actually eliminate this x3, and whatever incoming edges from this will be directed to here, and of course this will be no longer there. So this guy will be hanging, you have to eliminate it. So that is what has been done. You have taken this one from here, this one, all the incoming edges to this one are right to the left, because you are assuming that x3 is equal to 0. So everything will be directed over here. It had one path to the right which corresponds to x3 equal to 1, that you eliminate. So this is a sub BDD which is hanging, which you have to eliminate it, and then basically you are going to get a, if you eliminate it, this is what is your BDD will be looking like. Now utility I have told you, we may have another similar function. You want to find the equivalence of this or satisfiability, validity, whatever, by making x3 equal to 0. That means I want to see the behavior of some function or circuit if x is restricted to this one. So, this is a very important operation. So, like add, subtract, multiply, you can easily do by the algorithm I have told you for apply. Restrict algorithm I have told you, which is very obvious. Complement is a very obvious algorithm. Now, there can be lot of other operations on BDD like XOR, satisfiability, whether there exists, but everything can be implemented in terms of this basic operation. So, that is why I am not going into that. You have to take some combinations of this and you are going to find out a BDD which will actually take that implementation. XOR is very straightforward, there exists, for all. So, all such operations can be done by the way of this apply, restrict and your complement operation. So, basically before going to the high level decision diagram, let us come to again a gist what we have understood. Binary decision tree is very good, well accepted standard. Problem is that exponential complexity. So, not even a circuit with 10 gates or 10 inputs can be handled. What or can be verified rather, because a system with 10 input variables, the order of 2 to the power 10. Came to a boon is BDD. BDD will actually take up, basically you started with the explanation saying you take a binary decision tree is there, you keep on eliminating the redundancy, you are going to get something called a binary decision diagram. Compression is as high as 99% plus for most of the cases. So, BDD became a de facto standard of where you can represent all the systems in a very compressed manner. Now, the next question came is that from where I will construct the BDD? From a circuit or from a binary decision tree? By using Shannon's expression, we want to do it. The idea is that how you can build the binary decision tree itself is not possible, quite large. So, how we have to do? We have to go by the operation method. You take any circuit, take the input BDD, operate and get the final BDD of the output of the gate. Then eliminate the redundancy there itself, because I have shown you operation creates redundancies. For operation, two important things are there. The ordering you have to maintain, and after every operation you have to go and eliminate the redundancies. Here the redundancy will be slight, it will not be like it will become a binary decision tree. Slight increase in the number of leaf nodes and intermediate nodes may happen, which you have to eliminate. You have to keep on doing it after every operation. If you keep on doing it, never at any point of time your BDD will be larger. So, at every operation or after every gate, the output BDD will be small in size. So, whenever you get the BDD for the entire circuit, it will be within manageable limits. But still, how long? If you are going to go for a very big circuit like NOC and SOC, even the BDD is going to fail. People have found out that typically 100 input circuits, if you are directly going to apply BDD, there may be a lot of issues. So, they break up the circuit into cones of influence and some divide and conquer policy they do. But anyway, they cannot handle a very large circuit like a NOC and SOC. So, people said that we have to go away from the bit level to higher level. As we have already seen in case of testing, that we have to go from stacked faults or bridging faults to higher models of faults like which are more near to software engineering, and you have to go for register transfer level modeling. Similarly, in the case of binary decision diagrams. So, decision diagrams lots you can find out in the lot of papers, but the godfather is Bryant. He gave the idea of this compression. After that, people have used it for different kind of different type of decision diagrams like arithmetic decision diagram, high level decision diagrams, etc. And there are so many, but mainly in this class we will concentrate on ADD and HDD. So, the first one is actually called the MultiTerminal BDD. So, what is a MultiTerminal BDD? Basically, if you have a function in which the outputs are non-Boolean, generally we want to do some expression of 3 plus 5 and we want to show the answer in integer. If you want to go for BDD, you have to represent 3 as binary, 5 as binary, and things will start blowing up. So, multi-terminal binary, the idea is say that it is very similar. Based on the success of BDD, there has been several efforts to extend the concept to represent over Boolean variables, but having non-Boolean ranges. The first is something like that. BDD is very good, x is 0, x is 1, x2 is 0, 1, that is binary enumeration of the variables will be there, but the answer may not be represented in binary. It can be 2, 3, 4, 5 or integers. That is why they call it as a multi-terminal BDD. So, functions over Boolean variables, but output is non-Boolean. They may be integers or reals. Where they are applied? Many places like probability, technology mapping, program verification, arithmetic verification, etc. So many n number of places you may find out. Because if I represent the numbers in binary, size will be larger. If I can represent in decimal, the size will be smaller. So, therefore, they call it as a multi-terminal BDD, or sometimes people also call it as arithmetic decision diagrams, because you have at the terminals you are going to have basically the integers or real numbers. So, this was a very straightforward approach, keeping the variable Boolean. So, if you keep the variable Booleans, you can have the same branching structure like a BDD or a binary tree, or the same philosophy you can apply, but the number of leaf nodes will be more and will be more compressed, because if you are going for a binary, so 4 will be implemented by 100, 5 will be implemented by 101, and things will start blowing up. So that is what is the idea of multi-terminal BDD or arithmetic decision diagram. An example is better to illustrate, because operating on these BDD or multi-terminal BDD is also possible, compression is also possible, reduced ordering is also possible. All this stuff we have seen in BDDs are also applicable over here, but I am not going into the details because that is more involved compared to BDD. But the idea is similar. Take two nodes, operate, take the right child, maintain the levelization. The algorithm will remain same, but slight intricacies will come in. So those details we are not discussing in the course, but we are trying to give the philosophy how it evolved. So there is a function which is actually, you can see it is x0, 2x plus 3x. Now x0, x1 and x2 are binary variables, either 0 and 1. But 2 and 3 I am not going to represent as a binary, I will be keeping it as a decimal. So how the tree look like, it's very interesting to see. The tree is something like this, 2, 1 and 0, this is the level. So what I am having, x is equal to 0, x2 equal to 0, x1 equal to 0, x2 equal to 0, all 0, the answer is a 0. Because x0, x2 into 0, 3 into 0 is all 0. But if the value is x2 equal to, x0 equal to 1, x1 equal to 0, that means 2 into 0 is 0, x2 is also 0, 3 into 0 is 0, the answer is a 1. So 0, 0, x0, the answer is a 1. I will take some other path, it will be more interesting. Let us take the case x2 equal to 0, sorry, x2 equal to 0, x1 equal to 1, x2 equal to 0 means this one is equal to 0, x2 equal to 1 means 2, 2 into 1 is 2, and again x0 is a 0, so the answer is 0. So 0 plus 2 plus 0 is equal to 2, so this is the path, and you can see I have a leaf node which is equal to 2. Had it been binary, things would have blown up. Another interesting case, x2 equal to 1, x2 equal to 1 means 3 into 1 is 3, then x2 equal to 0, that means x2 equal to 0 means, sorry, this one is x1, I am extremely sorry, this one is x1, same levelization. So x2 is equal to 1, that means the answer is a 3, x1 is equal to 0, that means the second term is 0, so the answer is 0. Finally x0 is also equal to 0, so 0 plus 0 plus 0 is 3. So this 3 is a redundant node. So I could also have a 3a here, but actually I do not require a 3 over here because already the leaf node is there, redundancy is eliminated. So this is the way. Because another way I can get 3, because x2 is equal to 0, x1 equal to 1 and x0 equal to 1. So this term goes, 2 plus 1 becomes 1, so that is 3. So that is another path which is the redundant leaf node. So I am actually merged them, so you get the structure very similar to BDD. The architecture is very similar to BDD, the logic is very similar to BDD. Here I have only shown how the leaf node, because the maximum value can be 1 plus 2 plus 3, that is equal to 6. So the highest value of the leaf node is 6. So this is actually a multi-terminal BDD, you can express any kind of integers there. So the leaf nodes are not 1 but more, not 2 but rather more compared to each of the integer variables. But if you can see, the structure somehow looks like a binary decision, not a binary decision diagram, it looks like a binary decision tree. But some philosophy I have applied in the leaf node, so the answers are eliminated over here. So people actually started with, when people moved away from BDD to abstract level, they started something called a multi-level BDD, just like that. Philosophy will remain same, they will take a binary decision tree and they will start applying the philosophy of redundancy elimination in a slightly roundabout manner, not in as simple as we can do it in BDD. For multi-terminal BDD, the elimination of redundant nodes etc. is slightly non-straightforward. So you can, I will put up the references in the web, so if you want to see. But basically the idea is similar. You take a BDD, you can reduce the, if it is a binary decision diagram, concept of BDD will reduce the redundancy and make it compact. Same thing they have tried over here. They have started a multi-terminal binary decision tree, not a diagram. Then they will start reducing the redundancies and they will get a very compact representation which will be very synonymous to binary decision diagram but with multiple terminals. So that is what people call that as the arithmetic decision diagram. That is what is the idea. I have not shown the detailed steps of how redundancies can be eliminated except in the leaf node, but the structure is slightly involved because here is not 0 and 1, you are having multiple values. But still the same philosophy will be applied and you are going to get a very compressed structure. So that is one school of thought which actually started moving from BDDs to arithmetic or multi-terminal diagrams, that is more abstract or compact representation. So the problem here is that multi-terminal BDDs can implement a large range, because 2000, 3000, 4000 this integer can be there, but the problem is there is 2 to the power n possibilities, because it looks very similar to a, or the philosophy is very similar to a binary decision tree. But idea is that is what these are some extensions like edged valued BDD or binary moment BDDs. They actually take the philosophy of binary decision diagram and apply it on multi-terminal BDD and they compress it. And finally, people found out that such philosophy can be applied. You can get what you call, they call it binary moment diagram, not actually binary decision diagram, which is very similar to a binary decision diagram, well compressed, no redundancies, but you can still represent integers. But as I told you, this mathematics behind this is quite involved, so you can look at it. But in this course, we are just going to give we have given the idea how it happens by actually eliminating the redundancy at the leaf node, so that it can motivate you that the same philosophy can be applied. Rather, what we will go to is something, the most advanced version 1, which is actually called the high level decision diagram. That in fact, rather than trying with these binary variables itself, because in this case the x0, x1 and x2 are binary variables, rather than going binary and taking the output as decimals or real, the whole thing can be itself converted into a high level abstraction. That is the most advanced version of so-called, means most advanced means most published high level binary decision diagrams or high level decision diagrams is what is the most advanced, or it can handle the most complicated kind of circuits by the philosophy of high level decision diagrams, that not even the input variables will be binary, rather everything will be at the RTL level, at the C functional level or the Verilog level or the hardware definition level. So that is why we are going to look more into HLDD. So as I told you, BDDs and HLDD are good for rejecting digital systems at logic gate level, but whenever you go for abstract for system of systems like NOC and SOC, no way you can look at binary, you have to go at RTL. So the HLDDs or high level decision diagram, sometimes we call HDD, sometimes we call it HLDD, were introduced to mask that gap, that if you have a HDL representation or RTL representation, how do you go about it. So HDLs are very, very popular for high level and hierarchical test generation. It can be very easily, you can represent or model circuits at the RTL level. So it can be used for fault simulation, test generation, a normal means verification of circuits at the RTL level. So when we are verifying circuits at the RTL level, we assume that when the RTL level will be converted to gate level, the equivalence will not be lost, because nowadays from RTL to gate level conversion is more or less automated by some of the algorithms which Professor Chandan sir has already taught you, that espresso, 2-level minimization and so forth. So given the RTL, the gates can be always obtained by some straightforward algorithms which are known to be correct by construction. So we are not much bothered at the equivalence level at the gate, and in fact we cannot do that, it is infeasible taking consideration of the size of NOCs and SOCs. So what best we can have? We can have the equivalence checks at the RTL, and below that we assume that as they are more or less mechanized, so equivalence will be there. So therefore basically the Boolean values are now extended to basically high level means representation in terms of RTL. So that is why variables in form of Boolean values are now extended to vectors, Boolean vectors or integers, that is and Boolean functions are extended to data manipulation operations. That means we are all moving it from binary or Boolean level to functional level. Rather, I will just very quickly go into the mathematical definition, which I will try to deal with bit quickly, because this you can read it offline and understand what it means. Rather, I will focus more on examples. So what is a HLDD? So basically it is represented by this formula GDD. It has some nodes, initial nodes, some transitions, some functions within the nodes, some other variables like output function and all. So it's a 1, 2, 3, 4, 6 tuple. So now what is n? N is the set of nodes, n and n is the initial node, that is always there. Then n is partitioned into 2 sets. Here actually one important thing is there, here the nodes will have terminal and non-terminal nodes. Each non-terminal node has an expression called XPNI. So don't think about the mathematics, that you can read offline, just you think that it's a graph and there are some nodes are terminal and some nodes are non-terminal, that is leaf nodes and non-leaf nodes. And each non-terminal node will have an expression, and each terminal and each expression may be a control signal or a condition. And terminal nodes basically have a operation, and each terminal node is associated with an operation like add or subtract. And each non-terminal node basically is a control signal or a condition, like signal, input signal A equal to 1, input signal A equal to 0, input signal A is greater than B. Some conditions checks based on the input signals or the register values will be the non-terminal node. Terminal nodes will be some operation A or B, B or C, C or D, which will update the registers. It is something like, depending on some of the variable values like A is greater than B, A is less than B, that is more or less the register outputs, that will be represented by the non-terminal nodes. And based on the condition, some operations happen which update the value of the registers. So that will be represented by the terminal nodes. Just take it that way. Then there are of course transitions. They are represented by the transitions, and there is another important thing which are additional, basically compared to any normal finite state machine or DFA structure. There are some finite functions dependent on the non-terminal nodes to evaluate the expression associated with them. That is, the non-terminal nodes will have some functions like which I have told over here, which we will see why later they will be used. Then the expression associated with each non-terminal node Ni is evaluated by tau I. That means, if you have a non-terminal node, then you will have some expression internally, that is expression Ei, and there is a function, this one, which will evaluate this expression, and based on the evaluation basically you are going to take the outgoing transition. If this function on this expression is true for this path, it will take this, or it will take this, or all transition will have some fixed marker condition whose truth will tell whether it will go or not. That means, each non-terminal and expression is fixed. The function with each non-finite non-terminal node, it will operate on that, and then it will find out some answer. If that matches with this transition, it will fire, otherwise the other one, and so forth. And output of each node, as I told you, if you look at this, these are the two things I have discussed. They say that the third point says that these are some of the finite set of functions defined on the terminal nodes. That is, as I told you, each of the terminal node will do some operations. So this will be depending on that one. The operation associated with each terminal node is evaluated by the function. Now one more important thing, that is, each of the state will have a finite set of constants associated with the transitions. These are some of the constants. That means, as I told you, there is a state and there is some expression. This expression will be evaluated by this, and there will be some outward transitions. And the constants basically like x of tau 1, x of tau 2, this state is x, tau 2. Some conditions will be, or some constants will be assigned to each of the transitions. So if this expression on this function corresponds to this condition, this one will fire, otherwise this one will fire, and so forth. So this is where the things will go on. This is the mathematical representation. Just as we all define such complex mathematics before we go to a real example. So this is just the mathematical. Don't go just think that it is very complicated. It is just a mathematical way of representing an HLDD. So when I will just tell you the example, I will show you an example, things will become very, very clear. But when you are talking some formalism of decision diagrams, anyway you have to tell the formal definitions. So a transition basically from one node n tau to n tau plus basically is generally, it's always something happens that it will always from a non-terminal to a terminal, or a non-terminal to a non-terminal. So this is actually the initial tau, this is the final tau, and each transition basically we have some expression over here. This is a function and there is a constant x of tau over here, that is what is being told over here. So this one will evaluate this, and if this one will match this constant, then the transition is going to fire. That is what is being told by this formal definition. So the transition tau is said to occur successfully if the evaluated value of the association expression, this one on tau, is matching to x of tau. This is the capital tau, then basically that is what is being told over here. That if expression of tau evaluates to equal to x of tau, that means this is x, so this is x of tau, then this transition will take place. Example. So this is basically your graph. So as I told you, these are the non-terminal nodes, these are the terminal nodes, these are the terminal nodes. So now as you can see, each of the non-terminal nodes have some expressions. And sorry, this is the terminal node has a operation n4, that can be a1 plus a2, a2 plus a3, something like that. Non-terminal means some expression. So expression may be a1 greater than a2, or it can be just one signal itself like reset. So it will evaluate whether reset is true or not. And this x of tau 3 is a constant. For example, if I say that expression 3 is reset and this one x3 is equal to 1. So that means what? This transition is going to fire if and only if reset is going to be a true. That means tau of this one is going to be a 1. That means tau of capital tau of N1 node will check whether the reset signal is 1 or not. If it is 1, it is going to fire. Similarly, here I can say that there is a signal called hold. So capital tau of this of hold will be evaluating. Let this be equal to 1, x of tau 1 is equal to 1, and x of tau 2, this constant value is equal to 0. So this transition is going to fire if the hold signal is 1, and this one is going to fire if the hold is equal to 0. Now who is going to verify? This tau function which is expressed with this one. Here expression N0 is nothing but your hold signal. So it's very simple. Only the few slides I have shown before is the mathematical way of representation. So whenever you are going for verification, when you are going for any decision diagram representation, you have to go for the automata theory way of representing. So this is just the example I have told you. So it says that what are the set of nodes, these are the set of non-terminal nodes, N3 and N4 are the set of terminal nodes, what are the transitions, what are the constant values, this xi is the constant value. Then basically how this one tells that how the function is evaluated, like if tau expression evaluates with n, if the value of tau naught expression 0 is equal to tau of x1, then expression 1 will take place, otherwise the expression 0 will take place. That is what I have explained, that is written in this slide in text, so that you can read it when you are doing the lecture, because whenever we are telling the example it is simple to understand, but when you are trying to correlate mathematics with it, then it requires some slow phase of understanding. So you have to just read through the slide and try to correlate. Anyway, the notes will also be there. Just finally, before we close down with the decision diagrams, the example. This is a simple multiplexer circuit. There is a multiplier over here. So what it will multiply? It will either multiply in 3, and it depends whether in 1 or in 2 will go, because this is a multiplexer is over here, this is a multiplexer. So the multiplexer will actually tell you whether in 1 will go or in 2 will go, and the multiplexer will, this multiplexer will be either multiplying in 1, if selection equal to 0, then in 1 is going to come, it will be multiplying with in 3, and if this is equal to 1, then in 2 will come, and you are going to get the multiplication, and you are going to basically get the answer. So that is what is the circuit, and there is of course a register which will latch the value if the register enabled signal is equal to 1. Now internally you can see multiplier can be very big, it can be a 32-bit multiplier, so it can have multiplication values from 32-bit means 2 to the power 32 can be the range order of that. So you can understand even if it is a multi-terminal BDD, how many nodes it will have, infeasible numbers. So how it, but here it is only a simple structure because it is an RTL level. So the whole data path has been actually compressed. All this already we have basically discussed when we were discussing RTL level testing, that if in a data path if we are going to explicitly enumerate the numbers, it is just going to blow up. Even if it is a BDD, it is a multi-terminal BDD, forget BDD, multi-terminal BDD means to the power 32, even BDD fails for such high input size, and BDD never works for multiplier. It has already been seen that compression is always very good, but for multiplier circuit BDD generally does not work that well. Doesn't work means compression is not that efficient. So in that case basically anyway those parts aside, so here the multiplier is given as you have seen, but when you are taking RTL it is as simple as what I have shown over you, just 5 nodes, because it is at the RTL level means quite high abstraction, and in fact this is the only optimization, this is the only way of optimizing circuits, that is going from circuits bits to RTL level is only way if you want to model large systems like NOCs and SOCs. So what do you see, these are the 2 terminal nodes. This corresponds to the multiplication. Answer, I told you they are considered evaluation. So N2 into N3, and this one is N1 into N3, because as I told you there are only 2 ways of doing it. N3 is constant, it will be multiplied either with N1 or N2. Then next what? So these are the non-terminal nodes. So register enable is the expression behind this, and if I consider the function tau over here, it just checks whether the value is 0 or 1, just reads and find out whether the enable is 1 or not. If the enable value is 0, then register is just going to hold the old value. So therefore this terminal node, the expression is reg. This is actually an evaluation, a kind of a dummy evaluation, that it just retains the old value. If register enable is equal to 1, then only it is going to latch, so then I am going in this direction. If the multiplier select is equal to 1, that means this terminal is going to come in, you are going to get N2 into N3. So this is what is the expression. If max is equal to 0, N1 is going to come and the output is equal to N1 into N3, as simple as that. So even an RTL circuit, just you have to model it in terms of these high level decision diagrams, and but one thing I should tell you, it is not as convenient as BDD. Still now there is no very widely accepted result that it is canonical, or whether how it can be reduced, or how equivalence can be studied. So there are people are all trying to work out the good things about BDDs, canonicality, canonicity, order. If you take two orders, if they are equivalent, the system will look similar. Redundancy, if you eliminate, then you are always going to get a minimum structure for that function and so forth. So all things and operations on BDD, all the Boolean operations can be done. So now people are trying to find out algorithms that how those philosophies can be moved to high level decision diagrams. So as I told you that these are all not much, these are not much, I mean there is not much published work or well accepted works that how this can be directly mapped into the philosophy of BDD. They are all open problems. So one of the idea of doing this course is that to lead you into good research problems. So one of the research problem is that how you can verify large circuits at the RTL level, because at the gate level BDD is there, lot of tools are available over there which Professor Chandan has already discussed with you. But when you go for the abstract level, you will have a binary decision diagram or high level decision diagram, arithmetic decision diagram. But we are not, I mean such type of well established algorithms which will prove the canonical, that or the algorithms which are based on the properties of canonicity, or if the ordering is same, you will get into same BDD. So all those philosophies actually are not that way widely accepted or not yet published. So the idea is said that you have to go at the RTL level, you have to go at the high level decision diagrams. But what will be the exact structure of the high level decision? Something like this, or slightly something has to be modified so that the structure you are going to get is canonical, and if you take a same variable ordering, you are going, and if the two functions are similar, you are going to get a similar HLDD, which are the most important parameters required for verification, hold or not. So the research you have as a students, or I mean industry people or researchers, you have to try thinking in that direction, that how I will go for high level decision diagrams and still have the philosophy of BDD built in it. Okay, so this slide is nothing but whatever I have told you in English, that basically that how this BDD has been constructed is written over here. That is basically that is, it has first input is n, it is always there is a multiplexing in between those, then how basically which is the register enable signal, etc., and how the BDD is basically constructed, that is explained in these two slides. It tells that n naught is the initial number. So the two multiplication operations, this and this, are done by the terminal nodes, and all the non-terminal nodes basically have the signals called multiplexer select and basically the register enable. So that is the signals which corresponding to the non-terminal nodes. These are the operations which correspond to the terminal nodes. So whatever I have told you in the example is written in this slide, so that you can read offline and come out with it. One just before I close down, basically this was about the data path, because already when we have talked about testing, we know that data part is very difficult to do, because now 32-bit, 64-bit it starts growing up. But similarly there is also a control path. The control path can also be very easily modeled using BDD or HLDD, because if you have a circuit, one part you are modeling as BDD, other part you are modeling in HLDD, does not look good. So some people have also tried to thought that think how we can represent control paths in terms of HLDD. But control circuits are generally smaller, BDDs will suffice, but just they have given the example just to complete for the sake of completeness. So say that say some state which is present state, some control inputs are there, then the next states and these are the outputs. How do you represent? Very simple basically, obvious, it will be just like a case structure. So the initial node, and maybe this may be the S2 is it's this current state we are talking about, because for that example our present state is S2 and we are going to see what is the next state depending on the control variable. So this is the initial state, these are for state S1 and up to state Sn, we are just going to look at for state S2. So S2, this is a non-terminal node which corresponds to signal C1, there will be another non-terminal corresponding to signal S2. What are these terminal nodes here doing? The terminal nodes here will be the outputs, and what are the next state. So one next state is S3 and the other next state is S4. So in case of data path, the non-terminal nodes are expression and the terminal nodes are some operation, data operations, A plus B, A minus B, etc. But here they are basically which next state to go and what are the control outputs. So for example, if Cn equal to 1 and Cn equal to 0, you are going to get x3 in the next state and the output is 1 0 1 0. Basically that is what is 1 0 1 0 and the next state is S3. Similarly, if C1 is 1 and C2 is 0, you are going to next state is S4 and the control signals are 1 1 1 1. So basically that is what. So this is just a, I should not call it as a modeling, it is just a translation from the table to a high level decision diagram. But in fact, basically those things can also be done using a binary decision diagram also. You need not go to high level decision diagrams, because generally control circuits are generally smaller. The problem only happens with a data path. Already we have elaborated these things in the test module. So basically again whatever I have told you, now the control path has been designed, the high level decision diagram of the control path has been designed is written on this slide, you can read it. So anyway, this 2 lecture series actually brings us to the end of decision diagrams for verification. We started with binary decision tree, then we have seen for BDDs, then we have seen that what are the gains we have got, and in fact we should always be thankful to Professor Bryant who invented such a nice data structure. And in fact but as circuits started becoming larger, the bit level didn't work, then people started moving into arithmetic decision diagram, high level decision diagrams, etc. But the main philosophy still remains the same as BDDs. Reduce redundancies, first thing, and the structure should be canonical. What do you mean by canonical? The canonicity means basically if the ordering of the variables remains same and the 2 functions are similar, you are going to get the same BDD. That is what is a very, very important property of BDD. That is very much required for equivalence checking. So therefore, HLDD is a long way we have come from BDD, but still some main philosophies of BDD still needs to be proved on this. So as researchers, I want you to please think and work on those directions, and at higher level how we can have a canonical high level diagram, how I can do verification using those structures. Thank you. And in the next classes onwards, we will try to see how this BDD and HLDDs etc. will be used for exactly modeling sequential circuits or state machines, because this we have seen that verification main problem is we are getting stuck with the circuit, model size, state model size. The BDDs and ADDs whatever we have seen are basically showing how to represent the functions in a compressed manner. Now we will use that philosophy to model the states, that is basically called symbolic model checking, bounded model checking, where we will see how the finite state machines can be modeled using binary decision diagrams, so that the problem of explosion of the state space modeling of the model for verification is solved. Thank you.